Hello everyone. There are many situations where you need to georeference a layer to match existing layers. In this little video here I overlay several layers over a digital elevation model over the city of Lethbridge ending up on campus. And in order to do that I went to the tourist office and I got the city map from them and digitized it on a little digitizer back home and then had to georeference that. Unfortunately, before we can have fun with the georeferencing, we have to look into the details of statistics. A very important part of georeferencing is to understand and work with the root mean square error, RMSE. And that is automatically calculated in ArcGIS as long as you have at least 4 ground control points. So we need at least 4. And we need to have an acceptable error that we can calculate from the scale of the maps that we have available for georeferencing and ground truthing. And so we need to define the target RMSE, and if it's lower than the target, we can accept our results. If it's higher, we have to do some extra ground control digitizing. So here you see the basically scanned in ground control point versus the true control point where it would be. Not all points can perfectly fit the original. And so we call also this the residual. So this is basically the difference between the predicted and the observed coordinates, x coordinate and y coordinate, individually calculated. This would be calculated in meters. And so all we do is, if we have 4 ground control points, we have 4 different errors that we square, that we sum up, then divide it by 4. And this is why it's called the root mean average of this square error, the error and the square. So this is where the RMSE comes into play, and it is displayed during the geoprocessing process. So the next step, first of all, what we have to do is we have to calculate or estimate the accuracy of our map that we want to have. So let's do it. Before we start georeferencing, we need to have a target accuracy. How many meters on the ground accuracy do we want? That means we have to work with a scale of our referencing map to which we georeference. And let's just assume that we have a map scale of 1 in 50,000 of our most accurate map to which we want to georeference. So let's see how we can make that simple calculation. So let me just type here. So we have basically the distance on the ground, on the map, in this case is 1, and the distance in the real world is 50,000. And it doesn't matter which units we use, as long as we always have the same units. So let's assume this was meters. 1 meter on the map would be 50,000 meters in the real world. Or if we say 1 millimeter in the map is 50,000 millimeters in the real world. We have already discussed that the typical mapping accuracy that we can expect is 0.5 millimeter on the map. So let's just assume this now. So again, here the distance on the map is 0.5 millimeter. So that would be then the same as simply saying, so I'm dividing this by 2. 1 divided by 2. And again, let's have this in millimeters. And that means we divide this one here by 2 as well. And of course that's 25,000 millimeters. Now we want, in our case, when we georeference, we want to have it in meters, because we think better in meters in real world. So in real world, if we wanted to convert this to meters, That simply means we're taking this value here and divide this by 1000. There are 1000 millimeters in a meter. Divided by 1000. And here is your answer. Half a millimeter on the map at a scale of 1 in 50,000 equals 25 meters in the real world. So let's just have this as our final answer here. And let me highlight this. There we are. That's our answer. We can only georeference properly if we have known coordinates on the ground. Of course, we could use one of many available free base maps, and we can zoom in here. But in my case, I would like to use a topographic map that we can download for free from the internet. What we can do is we can then display it on the map. These are georeferenced, and let's just check out that they fit properly. So let me zoom into this corner here and wait for the refresh, and let's zoom in quite a bit so that you get the idea. So here in blue on the topographic map we have our UTM coordinates. 391,000 meters east of the meridian, the center meridian, and 5,511,000 meters north of the equator. So let's just double check that this works. I put my cursor down here, and what you can see now at the bottom over here, there you see the map coordinates. And if I go in here, you see that they are extremely accurate. 391,000 east and 511. In this case, I'm out by about 8 meters, but I haven't zoomed in really deep. And so that means overall that the map has been properly georeferenced. So we need to just make that little check to gain confidence that our final referenced map will be accurately referenced. Now let's find out where the scanned map is right now in our coordinate space. Let's zoom out and into Lethbridge. So somewhere in here should be our map. And if I now add here the scanned map, it's nowhere to be seen. It is somewhere else. We can of course zoom to this map, extend, zoom to the layer, and there is a scanned map, but it is obviously somewhere else. Now at the bottom of the screen you see here the coordinates, and if I go here to the bottom left coordinate, you see this is my 0, 0 point. What does that mean? It means that this bottom line here is right at the equator, and this whole area here, this line is right on our central meridian. And so obviously that's not where it belongs, and that is the reason why when we now zoom out, we're zooming out of the equator, and we will not be able to find Lethbridge and this map on the same display. But there is a good tool in the georeferencing toolbox that allows us to roughly overlay our TIFF file, our original ungeoreferenced file, over our geospace. One important part before we start the georeferencing process is that you have a really good idea about the extent of what is on the map. So in our case here, when we look here, there is the Highway River Bridge on the north side, so the river just goes a little bit north of that. And then we have the university here, bottom third. And then here we have our islands here that are near the golf courses. And so that's at the bottom left corner. So that helps us to zoom in into the appropriate extent that we want to have. And we can do that by simply going to our map and looking around and zooming in and out until we find something that we think is appropriate. So here's our High River Bridge on the northern end, and here are our islands, and so I think that's probably not a bad starting point. So in order to view them both, you start the geoprocessing tool. You do that by going to the imagery ribbon and start the georeferencing tool. And right on the first part here on the left side, there you see fit to display. So click on that, and now you see both on top of each other, and we can go back and forth. The scale is good, of course the location isn't, we'll sort that out. And we could also make now our map, our scanned map, transparent. Let's do that, then we can see them both. And that means now we are ready to select control points. Go back to Georeference, add control points. And we want to have control points ideally in the four corners of our scanned image. So let's use the C button so we can pan around. You see how the handle has just changed. Now I can zoom in here. I see the bridge drive intersection, and here I see the bridge drive intersection in red on my topo map. So I say from the scanned map, from the point source to the target, it's over here. I click on that and the map has already adjusted. Let's find additional control points. Again with the C button, pan where you want to be. Let's do an easy one here, the center here of Whoop-Up Bridge, the middle to the middle. I'm just doing a pretty rough digitizing right now, that fits quite nicely. Let's add one here in our neighborhood. I'm sure we can find some nice intersections, like this one over here. There's a one over here from the scanned map to the topo map. Further here from the scanned map. So there. So this intersection here is over there. So from the scanned map to the topo map. Much better. And let's find one in the northeast corner if we can. This is already pretty well lined up. We just need to make a minor adjustment. And we're going from the center of this intersection, or this one here, it doesn't matter, to the center of this. Not perfect, but let's find out if we have met our target of 25 meters or better. We can do this by adding the control point table over here, and there we see our digitized points. And what's really important here on the right side, the residuals, there you see the difference between the original point and the other point simply by interpolation of the control points. And we see that there are some points that are not very good. They're over 30 meters out. And what we can do is we can select this point and we can zoom into this one and see which point it is. It is the one on the bridge. It is a bit out. We can decide if we want to delete this point and maybe add another one. Just redigitize it. So add control point. Go to the center of the bridge. From here to there. And hopefully that control point, it's still out. But let's look at our RMS error altogether. You find this here half transparent in the top right, and let's zoom into this. And so here your total root mean square error is 21 meters. So that is less than our 25. So in a way, mission accomplished. Of course, now you could go in and delete a control point, add another one until you're satisfied with your georeferencing. And once you are happy with your georeferencing, well, then you have to now select which transformation you have. We only have 4 control points, or 5 control points in this case, that only allows us to do a first order polynomial or affine transformation. So that is the correct one. And now what we can do is we can save this map, update the georeferencing transformation of the source raster dataset, or we save it as a new file, so we can now create a new output file that would be our georeferenced TIFF file. When we click at Save as New File, there would be a suggested output dataset. You can rename this. There's your coordinate systems, correct. We don't need to transform. We could basically just hit export, but you have to understand a very important part in the settings. We could snap to existing rasters. We don't want to do this. Here is the key part that we have to be concerned about. It's called resample. And there we have our nearest neighbor, bilinear and cubic convolution resampling methods. And you have to understand what they do, and we discussed this in the lecture, but I want to show you what the results are using either of these. And it's very obvious that one is preferred over the other 3. I have processed the output in 3 different ways. One way was our nearest neighbor, the default setting, nice clear image, and it fits quite nicely. The second time, here is bilinear interpolation, which is pixelated and not recommended, obviously, and cubic convolution is slightly worse. You cannot even read the labels. So in this case here, the nearest neighbor setting is the right one. Don't always trust the default settings. If this was an air photo, a satellite image, then you may have to use another one. In some cases, cubic convolution is definitely preferred. So go and play around with the options. Once you've got your settings, sometimes just save them under their different options and see for yourself what gives you the best results. And the final check we want to do is we want to look at the attributes of our newly georeferenced scanned image. Let's go to the properties, and under raster information, same number of rows and columns, but here now we have a grid cell size of 3.27 meters, so about 3 by 3 meters, and if we look further under extent, now it is in meters. Before it was unknown. We recognize these numbers, about 5.5 million meters north of the equator, correct for Lethbridge, and our distance from the center meridian. And of course, now we also have a spatial reference, which we wanted to have properly georeferenced TIFF file. So having made those checks, we now can work with this scanned image, trusting its accuracies, etc., etc. A really good practical example is when I review environmental impact assessments, such as the one that we see here, an older one. All these documents are publicly available, so there's nothing confidential here. And these are very long documents, 944 pages in this case, lots and lots of figures, which I'm interested in adding to my GIS database. And here's just one example. If I go here to this watershed map and here the study area in this case, or the project area in red, I want to be able to download this file, georeference this file, so that I can work with this and maybe derive some other information from this file. So by further inspection here, I see that I have here coordinates. My knowledge of the area tells me that these are UTM coordinates. And so I know exactly the distance to the equator and the distance away from my central meridian. And so I can use this information, these crosshairs. So if we zoom in here, these crosshairs here, you see they give me the exact distance to the equator and to my central meridian, and there are lots of crosshairs around here, so plenty of very high quality ground truthing points that I can have. So the key thing then is you have to then select your file and basically screenshot or take it from the PDF and save the image as a JPEG file or your preferred graphics format, and then just bring it into ArcGIS. Here I have an empty map. The only thing that's added is my ungeoreferenced TIFF file that I just got from my PDF. And before we can do anything, we need to understand which coordinate system we are dealing with. And so when we look at the details of the figure at the bottom right, we can see that it is in a UTM zone 12 coordinate system using NAT 83. So we're all familiar with these projection information. So all we need to do very importantly is to set our map display to the same coordinate system. We know how to do that. We go to properties, we go to the coordinate systems, and we now select our respective one. So in our case it is a projected one, it is NAT UTM, NAT 83, and we set UTM zone 12. There it is. I say OK. And now the map display is set to that coordinate system. And now we can go and add control points. Now we can georeference. We go to imagery, georeference. We can go straight to add control points. We need nothing else. All our information is here. And now, of course, what we want to do is we want to really zoom in. In this case here, let's have a look at the numbers. So I have an easting of 487,000 and I have a northing of 6,306,000. So let's zoom in, and you want to zoom in as much as you possibly can. And so now you go to the center of your pixel, that's as good as we can make it, and you click your from point. But instead of now adding a point from a map, we can right click and add our coordinates straight here. Our X or easting was 487,000 and our northing or Y was 6,306,000, and we hit OK, and we can zoom back to the extent of our layer. There is our control point up here, and now we can choose a second one, a third one, and a fourth one up here, and then after that hit Save New, and there's your new georeferenced file. I hope you enjoy your GIS journey. See you next time.